lower survival rate than low LET. The alkyne curve, this assumes that there's no changes in oxygen concentration. So the alkyne curve looks at fractionation of doses. So if we take a look at this example here, if we have a single dose, we follow the green line down here, line number A. A single dose will get, again, a lower survival than if we fractionate a dose. So we split the dose into two parts, and then we can get this shoulder coming back into it and for the second dose, and so we get a much better survival rate of cells. And so curves B, C, D, these are for examples of different kinds of cells. Now the next thing that can affect cell survival is the oxygenation of the cell. So tissues and cells are more sensitive in the presence of oxygen than they are when they're hypoxic, which means low in oxygen. The oxygen effect is really important in radiotherapy because quite often tumours have areas of hypoxic cell, and so they're actually harder to kill. Diagnostic X-rays are conducted under full oxygenation conditions to increase the radiosensitivity of the tumour. So the oxygen enhancement ratio, the OER, it's an important mechanism in the context of killing cells in radiotherapy. So oxygen is a dose modifier, so you can actually increase, well, effectively increase or change the effect of a given dose by having oxygen in there. When we're talking about oxygen, it has to be elemental oxygen, so O2 inside the cell, not oxygen as part of another molecule, for example, not as part of water. So if you remember back to the indirect effect from last week, this is the effect where radiation enters a cell, causes free radicals to be formed, and so, for example, H2O2 inside the cell, and then these molecules or these free radicals are then what goes on to damage the DNA. So this is what an indirect effect is, and so if you have more oxygen there, you can form more of these free radicals, and so it's actually how, and that leads to the greater radiation damage done. And the reason that the indirect effect is so damaging is, again, going back to this figure that we had last week, the DNA molecule is very long, but packed into a very small area or small volume, and so it's packed really tightly. So then if you have a form a free radical by irradiating the water in the cell, if the free radical is able to live a long time, so for example H2O2, then it has a much better chance of interacting with the DNA than say a short-lived free radical. So in a tumour, so a tumour contains a lot of cells, and sometimes tumours grow very, very quickly, and in fact so quick that they can't actually get a blood supply to all of the cells. So, so there's no, so some sections of a tumour might not have a capillary supply. And therefore some areas of the tumour have acute hypoxia, which means that there's not much oxygen getting to it, or if it's chronic hypoxia, it means the cells are far too far from the capillary for oxygen to actually get to them. So, for example, if we look at this diagram here, we can see up here we have a blood vessel, and it's we're not using English here, but that's okay. So we've got a blood vessel here. We've got some cells here which are oxygenated. We've got so the oxygen flows through these cells, but it can only go a certain distance and is absorbed by all of these cells up here. But at some point there will be insufficient oxygen flowing to these more distant cells, which means that they will be slightly hypoxic, and then eventually some cells are so far away that they don't get any oxygen at all and they die. So the oxygen effect, this means that if you irradiate these cells, particularly in like a radiotherapy context, these cells closer here all have high amounts of oxygen, so they're very sensitive to radiation. But these cells here, because they're hypoxic, they're less sensitive, so you'll actually get less cell kill with these. So this is actually a harder tumour to deal with or to treat. So if you fractionate your treatment instead of giving the dose all at once to a hypoxic tumour, what will happen is, because these cells here are high in oxygen and will get killed off easily in the first fraction, what will happen after that is that the cells will die off and the tumour will shrink, and then therefore the oxygen can travel further through and start reaching, for the second fraction, start reaching some of these cells. And then that way, if you fractionate the treatment over lots and lots of fractions, you'll eventually get a dose to all of these cells here. But the oxygen effect is LET dependent. And so, for example, if we look at this slide here, we've got low LET radiations here, and we've got high LET radiations here. And you see that there's actually a different effect of oxygenation. So, for example, if you have a look at neutrons, there's interest in using neutrons as a radiation therapy treatment method, because it's better for treating hypoxic cells, or easier for treating hypoxic cells. The oxygen enhancement ratio is the ratio of doses which produce the same level of biological effect in hypoxic cells compared to oxygenated cells. So this can get a little bit confusing, and sometimes in the calculations for this, people actually get the calculation upside down. So the OER is, we'll look at the top one first. Dose necessary in hypoxic conditions to produce a given effect, divided by the dose necessary under aerobic conditions to produce the same effect. So we're looking at the effect here, so this will be cell kill. The other way is cell kill in the presence of oxygen divided by cell kill in a hypoxic environment. So let's have a little look at an example here. If we have a tumour control dose is 106 gray when the cells are hypoxic, but the tumour control dose is 40.5 when it's not clamped, so it's got oxygen. What's the oxygen enhancement ratio? So this is just the dose necessary in hypoxic conditions to give a given effect. So this is 106 gray there, divided by 40.5 there, and we should get 2.6. But what if you get a question which is worded slightly different? So we have this one here. A radiation dose produces a cell kill of 75% in oxygenated conditions, but only 25% in hypoxic. What's a oxygen enhancement ratio in this case? So this time, the given effect is 75% cell kill. To get the same cell kill in hypoxic conditions, and there's an assumption here that there's a linear dependency, you'd have to increase the dose by 75 on 25. All right? So we're after the 75% oxygen kill, the cell kill, but what do we have to do to get the same in hypoxic conditions? And that is, you have to get this 75 up to 25 up to 75, and so to do that it actually becomes an oxygen enhancement ratio of 3. So if you get a question that looks like this, make sure that you get it right. Easiest way to check is it's always going to be greater than 1.